Welcome to our podcast. My name is Peter and I'm a sales engineer here at HAWE. Our question today is, do you know how a typical bending cycle on a press brake looks like? And to answer this question, I invited Martin. He is our key market manager for machine tools and presses at HAWE. Welcome, Martin.
Yeah, thank you, Peter, for that kind introduction and fascinating question.
First of all, Martin, what do our listeners need to know, or what information is most important for us in order to be able to talk about the bending cycle?
Yeah, Peter, first of all, you need to have in mind how a press brake itself is designed. You have a fixed lower tool, this so-called die, and then you have on a movable upper beam, you have the punch assembly to it. And these two, the punch and the die, works against to each other. So I think that's very simple. The bending cycle itself is divided in roughly 6 phases. You start at the programmed TDC, the top dead center, and then you go over to fast down phase. You have the mute phase. You have the working speed phase or bend mode. Then you go over to decompression phase. Then you have the retraction phase, and then you're back at TDC and so-called idle. You can switch the parts or go over to another bending step then right there. But this is typically how it works, always the same time, every bend works like that.
Very exciting. But some question came up for me right away. What are typical fast down speeds?
Well, for the fast down speed, we need to know that how the press brake itself works in a fast down mode. In press brakes, you use the weight of the beam and the gravity force itself to bring down that beam, and so the weight of the beam is important how fast your press brake can come down. And so typical fast down speeds for a 170 ton press brake are roughly 200 to 220 millimeters per second. When we compare these speeds with a 800 to 1000 ton press brake, then you have roughly 100 to 120 millimeters per second. And this is because you have much more masses there, or the beam is much heavier there. You have these higher masses need to be controlled, and you have also higher flow rates over your control blocks. And so therefore it's okay if you go stroke like 200 millimeters per second, not in 1 second. You can do this 200 millimeter stroke also in 3 to 4 seconds. And so that's okay. So that's how the fast down speeds differs.
Okay, that means fast down speeds depend on the weight of the upper beam and the size of the press brake, and are typically more than 200 millimeter per second.
Yeah.
You mentioned the phase mute point. What does it mean exactly? And is it always at the same position?
Yeah, good question, Peter. The mute point itself is easily said just a switch over or a switching point, let me say. For the fast down, as I already mentioned, you use the gravity force to bring down the beam. So you have a pre-fill valve there to fill up this big volume in your cylinders with oil. And at that point, at the mute point, you need to be sure that these pre-fill valves are closed, and you can go over with your proportional valves, for example, to bend actively the part there. And so that's about the mute point. Well, answering the second part of your question, if it's always on the same position, well, it's not. It always depends how the worker programs its cycle, and also it depends on which tooling is used to bend the part.
Mm-hmm. Okay, I see. The mute point is a transition from fast down to working speed and depends on the programming of the tool and the part to be bent. What are typical working speeds?
Well, working speeds, therefore you need to know that in Europe we have a C standard. The C standard, DIN EN 12622, is that C standard for press brakes, and it says that if an operator is in front of a press brake and is bending the parts manually, then you must not exceed 10 millimeters per second at working speed. So this is because of reaction time of humans and so on. But if you put a robot in front of a press brake, then you can go up to 30 millimeters per second bending speed.
So the working speeds are typically 10 millimeters per second in operator mode, and in robot mode they are 3 times faster. Okay. One last question. Could you describe the decompression phase and why is it so important?
Yeah, the decompression phase itself is necessary because when you put in mind that you bend thicker parts even, and you have high pressure, high forces in your cylinder, and even that high forces deflects your machine frame. And to go over then, when you reach the bottom depth center, as I called if you reach the correct angle as it's programmed, and you want to retract to go back to the TDC, then you need to bring out that high pressure in your cylinders to avoid just easily switching bumps at that point. And yeah, so that's important to go over from the bending mode over to retraction or fast up phase.
Tip top, thank you, Martin. I think we've learned quite a lot today. Let's briefly summarize again. The bending cycle has 6 phases. We have a fast down cycle and a working cycle with different speeds. After the bend, the tension in the machine must be released and the high pressure must be released in order to avoid switching bumps and damage to the machine. After that, we can go on to the return stroke.
Yeah, good summary. Thank you, Peter, for that.
Okay, thank you very much to our listeners. In the meantime, if you have any questions or suggestions for topics, email us at podcast@hawe.de. Thank you, goodbye, see you soon.
Goodbye.